The city, a vast repository of stories, each one branching out like the threads of complex code. They say every commit tells a story. So, what's my story? Failed developer turned cop? Couldn't write code, so decided to pick holes in others? Maybe it's me. Maybe I'm the issue in this Reposa city. All I know is I'm the city's most trusted InvestiGITor. Lately, something's changed. Whispers say there's a new kingpin in town, pulling all the strings from the shadows. Goes by KB. Whoever it is, they are the kind of criminal that doesn't leave fingerprints on the keyboard, just a trail of cryptic commit messages and coerced histories. Anyway, this city is my home directory, and I'm here to clean up the code smells and corrupt blobs, no matter how many conflicts I have to resolve.
Welcome, ladies and gentlemen. Thank you. To Crime Scene InvestiGITor, the case of the naughty commit. Welcome to cadets to your very first day of Detective Academy. Now, I know you've all just graduated from basic police school, but you're in the big leagues now. You're in my house. I'm gonna teach you how to become a proper Git detective. Who am I? I am Chief Inspector Detective Kadel, and I am a principal platform engineer for a company called Babel in Berlin. When I'm not androiding or platforming, I love Terminal, Bash, and got really obsessed with Git. Now, if you enjoy any of this nonsense that you see here today, and you want more of this nonsense, then maybe check out my YouTube channel for extra crap. Now, as it's your first day of Detective Academy, we have a full-packed schedule. To begin with, we're gonna do a quick make sure everybody's on the same page of Git, an introduction to. Then we're going to do something very exciting. We're going to go to a mock, fake crime scene, and together we're going to solve a crime and bring a dirty criminal to justice. Now, everything you see here today is well documented in a huge collection of links in this Linktree address here. Feel free to take photographic evidence of anything you see, including my handsome self. Make sure to tag me on socials. But if you miss something or you're like, I didn't catch a photo in time, then please don't panic because the slides themselves are on the Linktree as well. Now, something very important to me. I'd like to introduce you to somebody very special. My partner of many, many years, Detective Refi.
Hey, nice to meet you, folks.
Refi is a fantastic sidekick. He is the Robin to my Batman.
Despite what this guy says, I'm the real brains of this duo. Somebody's gotta keep Detective Kadel from walking into open manholes.
Refi, that was like 2 or 3 times most. Thank you for making me look stupid in front of the cadets. Anyway, Refi has our back, and he is very trustworthy. Now, before we dive in, the work of an investigator is not about assigning blame to an individual. No, it's more about finding how, when, and why a problem occurred in your Git repository and having the correct and powerful skills in order to solve those Git issues for your team quickly. Good? Ready, cadets? Let's begin. Spin move. We'll get rid of this. It's just gonna, safety hazard. So Git is a version control system. Hopefully you knew that. It stores changes to your folder, your repository over time in these theoretical, hypothetical containers of change called commits. Now these are visualized by circles in this presentation. Every commit has a unique ID that's actually a SHA-1 hash generated from the contents of the commit itself. Okay, boring. Every commit has an ID. Great. Every commit also knows about its parent commit, so the commit that came before it. So in this case, C knows about B, and B knows about A. And this creates something called a DAG, or a directed acyclical graph. It's basically just a fancy way of saying you can pick any moment in time, and through the lineage of commits, find your way back to the start of the repository. So every commit knows about its parent commit. Also, somewhat obviously, hopefully, merge commits know about their parents' commits because they came from two. Good. So we know about commits, these containers of change, but there's two other object types that Git uses to recreate your folder structure at every moment in time. And these are trees and blobs. Sorry, okay. Focus, ADHD. These are trees and blobs. And you can think of it like this. Every commit contains one tree reference. So a commit is the container, the snapshot in that moment, and then the tree is the printout of the root directory of your project. So a tree is just like what's in that folder. So then a tree object can contain more tree objects, aka subdirectories in your project, or blob objects. And you can think of those as the actual files, the content of the files in your repository. And with this collection of these three different object types, Git is able to recreate your project at any moment in time. But where are they stored? It's very theoretical so far, right? These objects actually exist on your machine. Inside of every Git repository, there's a .git objects folder. Inside of every Git repository. And inside of that folder, living happily side by side, are all of your trees, commits, and blobs. Yum. So they're on your machine, right? Let's just take a quick sidestep to understand how Git turns your code into some of these objects. Let's take a blob object, for example. When you use git add, in that moment, Git takes the contents of your file and it hashes it. So it hashes it into a SHA-1 hash to create that ID. Put that to one side, we'll come back to that later. Then it goes to the contents of the file and compresses it down using zlib to make it smaller to store on disk. And finally, it goes to the .git objects folder. It takes the first two characters of that SHA-1 hash and makes a folder, a subdirectory out of it, if that folder doesn't already exist. And then it takes the compressed contents and puts it in a file called the remaining 38 characters of the SHA-1 hash. Weird. Detective Kadel, why are we doing that? Well, this is one of many Git efficiencies and why Git is so brilliant. Imagine a world, if you will, where this objects directory just has all of the objects in one folder side by side, hundreds, maybe thousands of objects. Every time that Git does something Gitty, it needs to index through all of those things. However, here, with this method, it needs to index through a maximum of 256 subdirectories because of hex. And from that subset of directories, then a smaller range of actual object files to index through. So it's an efficiency. Let's move on. Could we? Thank you. Cadet, Detective Academy, it's serious business, right? So if we know these files exist on our machines, can we interrogate them? Can we cat out these object files? Well, no, because it's compressed gobbledygook nonsense. But we as professional detectives need some tools to interrogate and manipulate these objects. And luckily, Git itself provides us with such tools. Now, we're going to learn about these tools, these Git commands, in the Git CLI way, Git command line. Just out of curiosity, raise your hand if you use Git from the command line often. Okay, good. I see you. I see you. Good. I also see those of you who didn't raise your hand. If you can stay after today, we're going to have a talk. Okay. No, but good. The reason that we're covering Git commands is because it's kind of, quotes, the hard way. Not really, but the hard way. So that you understand deeply the concepts. So when you go back to your gross, disgusting GUIs, like your source trees, your towers, whatever, you'll understand deeply the concept behind that button you're clicking. Father? Everyone else is hearing that, right? Or have I just lost it? It's very possible I've lost it. Right, out of curiosity, does anybody know how many Git commands there are in existence? Just yell out a number. Anybody? There's no wrong answers. Well, there are, but 24, a bit higher, more? I couldn't hear that, but that sounded good. Yeah, that was a number. Cool. 10. There's more than 10. Good. There is exactly, well, roughly, 149 Git commands in existence. They can be split into two categories. Porcelain, you can think of as the nice, friendly, user-facing commands that we use to interact with the Git system, like add, commit, branch, etc. And then there's plumbing commands. These are the scarier, dark, back-end commands that Git itself uses to do Gitty things and are really good when you come to writing Git scripts. So, two types of categories. Now, we know there's tools, there's Git commands that can help us work with objects, so let's see some of them. If we want to simply list all of the objects in our repository, we can use the revlist plumbing command with these flags. And we see all of the objects. Great. But Detective Kadel, you silly Billy, you did something stupid. You had that readme blob twice. No. I did this on purpose to remind you that Git stores changes over time. So the bottommost readme might be how the readme file started. And then the one that's two above it might be a change further on in the future of the repository. Tasty. Okay, so we can list them. What about reading them? Remember, we can't cat out these files because they're nonsense, but we can git cat file. Nice. Which basically turns those objects into something we can deal with. There's two main modes of operation. -T for type. So you give it a hash, and it says, that's a commit, that's a blob, that's a tree. Boring. The better one, and the cooler one for detectives, is -P for pretty print. And it basically gives that object back out in human readable format. Let's give it a commit hash. Look at that. That's familiar format. That's a commit message, an author, a parent commit. Remember I said all commits know about their parents? There's the proof. I'm not crazy. And, all importantly, that tree reference I told you about that points to the tree object of the root of the repository. Ooh, let's take that hash and put it into the same command. We get this output. It's as though I've sort of LS'd a directory, LS'd a folder. We're seeing blobs and trees, or files and subdirectories. So let's take one of the blob objects and put it into the exact same command, and we get, finally, plain text output. Your code right back at you. Now, if any of this piques your interest and you'd like to learn more, then great news. A very handsome cave explorer took a very passionate group of cavers about 2 years ago into a cave system called the .git folder cave. Yes, the .git folder cave. He took those expeditioners into the cave and learned all about how Git works under the hood, and you can learn more there. The videos are available on the droidcon content website and on YouTube.
Detectives, there's been a horrific crime.
Okay. Detectives, I know we promised you a fake mock crime scene today. Okay. But I guess there's nothing better than a real crime. It's a shame it has to be so brutal on your first day. Okay, just when you go past the tape, just hold on to yourselves and I'll see you on the other side of the tape. Good luck. It was broken unit tests! Oh God. Oh, are you okay? Oh, Jesus. Oh my goodness. Yeah, this is barbaric. I'm sorry that you had to see this on your first day. Something so gruesome on the screen.
Who would do something so barbaric?
Referee, I have no idea. But it's days like these that remind me why I became an InvestiGITor. Let's catch a criminal. Spin move. Now, Refi, to begin with, we need to sort of go back in time. We need to sort of go back to when the crime was committed so we can understand how and why.
Hey, dreamer, come back to reality. It's not like we've got access to a time machine.
Refi, you know we do. And it's called Git. Because Git stores changes over time, meaning you can go back to any moment in the past and recreate your repository, your folder, how it looked then. And there's 3 modes of time traveling I'd like to talk to you about today. 1, the just visiting variety. Jump back in time, have a little look, and then return to the present. There's do and undo, or flip some changes you've done previously. And there's danger mode, going back in time, but a little bit more permanently. We're going to look at each of these modes. I'm going to give you a command that you can use to do it, and then a visual demonstration because I can't understand the texty version. I learned through visuals, so maybe you do too. So just visiting, we use the git checkout command to jump back to that moment. Usually we use checkout to switch between branches, but git checkout can actually take any sort of git ref, and that's just a sort of fancy word for a nickname for a commit, a moment in time. It could be like an actual commit hash, a relative reference like head or head -1, etc. This is the visualization. Just to explain what you're seeing here, there's a very basic commit history here. There's head, where we're pointing to now, what we're looking at now. If we're in a tip of a branch, it'll have the branch name above it. And for full clarity, in the bottom of the screen, sometimes there's .git files, actual files that are in your .git folder that are changing when you move around, just for full clarity. So you can see the head file, for example, and a refs file, whatever. So, let's go back in time to C. We're going to visit. Just check out C. Our head will pop over to C. And the head file has changed. It's no longer a refs head main. It's just the commit hash. Weird. And we're in something now called a detached head state, which is a really weird, scary way of basically saying we're not at the tip of a branch anymore, Total. Okay? When we're done having a look around, we're now seeing C how it was. When we're done, we just check out our branch name and jump back to the present. Easy peasy. Now, do an undo, or it's rewind time. It was my Will Smith impression. Git revert, amazing command. It basically takes some changes you've done in the past and flips them over, does the complete opposite. Again, it takes a ref, so a moment in time. Let's visualize it, it's easier. Imagine if I wanted to revert E, so the commit I'm on now. What git revert will do is create a new commit, updating our branch, actually going forward in time, commit F. But commit F is just the mirror image of commit E. So if E's diffs were minus startup, add cleanup, then F's diffs are add startup, minus cleanup. So it's a really great way to undo something you've done in the past. And finally, danger mode, my very favorite. This is like git checkout, but also updates your references, updates your branch as well, right? It's a little bit more permanent. And it does something different with the changes. I'll explain better now. Git reset, again, takes a ref and a mode of operation. It has 3 modes. And these modes basically just affect what happens to the changes. The visualization is easier. Words is complicated. Pictures is good. Here's a demonstration. Let's reset soft mode to C. Immediately, my head jumps to C like it did in the past. My branch, however, has updated. I'm still at the tip of main branch, so the branch has been updated. The changes from D and E, right, that we've just sort of gone past, are taken and lovingly placed into the staging area. That's as though we've typed the changes, saved the code, and then used git add to inform Git of their existence. Mixed, which is the default one, does the same thing, jumps back, branch update, head moved. The changes from D and E are taken and lovingly placed in the working directory, as though we've typed the code and saved it, but have yet to tell Git about it. And finally, you've probably guessed the last one, hard. Same thing, but the changes are drop-kicked out of existence. And that's why people say that this time, this one's a little bit dangerous, but it really isn't to us Git detectives when you understand one of the biggest concepts of this talk, of Detective Academy. And that's the theory, or the concept of unreachable commits. Right now, our repository, it looks like D and E are lost to us forever, but they're not. They're just not accessible via the usual branch system or tag system. They are unreachable. They're sort of dangling in the ether, but they're still there for now. They're just not accessible, but those objects that make the commits, trees, and blobs are still on your machine for now. So here's a better visualization of what it really looks like. D and E are sort of disjointed from the branch there, right? What if we wanted to get E back? We can bring it back from the dead very easily by just using git checkout E. And we check out that commit and our old changes are back in front of us. Again, we're in a detached head state because we're not at the tip of a branch right now. But we can fix that by simply creating a branch from where we are. Easy peasy, and our changes are back. Nice. But Detective Kadel, your example was very easy. It was 1 letter for you. It was E. But what do we do when we're in reality and we have 40-character long hashes that we need to pass in instead or find? Well, I've got you covered. One of the greatest commands that will save your ass every single time is the git reflog command. Now, if you don't know about it, then I'm very grateful to be able to educate you on reflog. As you're moving around Git is keeping a log of every time your references update. So every time your head changes, that's an update. Every time your branch changes, update. Every time you do a bunch of different actions. So you can use the git reflog command to dump out that log of information. Now, back in our situation, all we do when we were like, how do I get E back? We use reflog. We look at the top line, that's where we are now. So we look at the line beneath it, that's where we were before. So I can just take the hash in the far left column, and bada bing, bada bip, we've got E. We're back to reality. But Detective Kadel, you said that those unreachable commits are still there asterisks for now, until something happens. And that thing is possibly garbage collection. Now, Git has a very sophisticated garbage collection system that runs automatically on a bunch of different moments. You can run it yourself with the gitgc command. The reason we're talking about it is not because of this, but this is its main objective. Gitgc takes the way we've currently been storing objects, which is called loose objects. They're sort of just jangling around in that objects folder, and it deletes them and turns that information into something called a pack file. Now, pack files are chef's kiss good, but we don't have time to cover them. So again, I will point you back to the very, very handsome, very, very modest cave instructor from 2 years ago, because he went deep into pack files and explained how they are the winner of the version control game. Anyway, for us, we're talking about GC because it possibly might clean up unreachable commits. You'll see that later. We've got a problem, Refi and cadets. We've just been jumping around randomly in time, trying to find this criminal. There has to be a better way. It's my favorite bit.
And this search is gonna take a lifetime. It's like looking for a needle in a haystack.
Yeah, Refi, it's because we've been just randomly going back in time, guessing when the crime happened. We need a tool to help us figure out when it happened. And we have just the tool. It's called git bisect, and it's an amazing command. Bisect meaning to cut or divide into 2 equal bits. Git bisect essentially performs a binary search on your commit history, because it's ordered history. And it's looking for, well, whatever it is you want to look for. In our case, we're looking for when the crime happened, when the unit tests first broke. That's easy for bisect. Let me show you how. Here's our simplified commit history. We're going to type in git bisect start to tell Git, hey, Git, weird shit's about to happen, bro. You're about to jump around a bunch and help me find this thing. And Git's like, yeah, let's go. Then we tell Git 2 pieces of information. First, we tell Git good and a ref. So we tell it a commit that was good, and that's the latest that we know for sure the tests were still working. And then, the flip side of that, we tell it a bad commit, and that's the earliest that we know for sure the tests broke. And what this does is give Git a smaller range to work with in this binary search instead of the whole history. But you could do the whole history if you're crazy. Anyway, then Git jumps into action. It immediately, without any warning, checks out the middle commit in that range, and it just sits there, looking funny at you. Because now you need to tell Git something. You need to say if this is a good or bad moment. And how do we find that out? In our example, we run the tests. So, run the tests, and this time, they passed. Great. So I tell Git bisect good. Immediately, Git checks out again, but it was able to eliminate that last commit we were on and everything to the left of it. Remaining range, checks out the middle commit, waits for an input. We run the tests. This time, the tests failed. Oh. So we type git bisect bad. Git is not able to eliminate this commit, but at least everything to the right of it, it knows it can't at least be this one. And finally, the remaining commit, we run the tests. This time it passed great. Immediately, Git is able to say, whoa, F. F is the first bad commit. Good golly, F is the one where the crime happened. We then use git bisect reset to say, hey, Git, calm down, buddy. Take me back to the tip of the branch. We're leaving crazy mode. And we've got it, Refi. With just a few simple jumps, we were able to figure out relatively easily when the crime happened. B99. B99 is our naughty commit. And let's look at this commit message. Made some good changes. Ja klar. What does that mean? We should have seen that coming. But the great thing about Git is that everything's logged. We can see even the, using the git show command, we can have a look at the diffs of the, oh God, I'm so sorry. I didn't mean to put that up on screen so vividly. Again, that's the brutalization of the unit tests that caused the crime. Please don't look too hard at that. You will feel not well. But the best thing about Git is every commit has an author. So we can just look at, they have obfuscated their identity.
Versus. Thought we were hot on their tail. Looks like the perp's gonna get away with this.
1 second. Okay, we're action stations. I forgot what you just said, Reffy, but hang on. Don't worry about it, because look at this. I've just seen something, Reffy. There's a file here in B99 that isn't there in the present. Someone has been destroying evidence. Now, cadets, I know this is a very difficult time. There's been a horrific crime, and you're probably feeling a little overwhelmed on your first day, but it is tradition for the cadets, their first day, to take a class photo together. So we're gonna do that for tradition's sake, so we can put your photo up in the Hall of Legends when you graduate, okay? So if you want to be in the photo, please be in the photo. If you don't, hide your face or something. It's gonna be blurry. Here we go. Photo, cadet class 2024. Look at your, okay, hey, sensible now, please. There was a crime happened. You guys are messing around in a photo. Can't believe it. Okay, Reffy, so this is very exciting. In the present, we have no secret.txt file, but back in B99, we do. So somebody has tried to delete this file, but hasn't done it very well. Let's look at the file. Let's see if there's any clues for Okay, it's compressed gobbledygook nonsense. Fine. Reffy, let's send it off to the techies and we'll continue our investigation.
Partner?
Yeah.
Out of pure curiosity and educational purposes, if the perp had been smarter, how would they have properly disposed of those secrets?
Well, Reffy, I kind of like your thought. Because in order to catch a criminal, we need to think like a criminal. So yeah, let's figure out how we would properly destroy this secret evidence, and maybe it'll give us a new lead. Here we go. The problem that we've got, in B99, there was this file, and somebody just simply deleted the file and committed the changes. But as we know, Git stores changes over time, so the blobs, commits, and tree objects that made up the changes are still there in the Git database. Ugh. And there's another problem, in fact. Just on the perp's machine itself is one thing, but when the perp pushes their changes, other criminals, other developers will have those secret files and secret blobs on their machine too. Not great. So what we need to do is essentially rewrite history. We need to go through each commit, check if the secrets file is there, and if it is, delete it, and then overwrite the commit, destroying the other one from our history. Sounds complicated, but we have a tool for the job. And it's called Git Filter Branch, the terrifying Git Filter Branch. Oi, oi, oi. Now, immediately the man page for Filter Branch is like, warning, warning, plethora of mangled histories, destruction will follow. And yes, it is a terrifying command that can cause a lot of damage in the wrong hands, but we, as professional detectives, we're going to deeply understand this command very quickly so that you're not scared of it anymore. Now, up front and honest, if you're doing secret removal and you want a really boring, easy time, then there are alternatives. And in fact, Git itself recommends this Git filter repo alternative. So just to be up front, but we're going to go into crazy mode and figure this out. So at the start, filter branch takes one main argument, a rev list, and that's just a range of commits, And the default is the branch you're on, hence the name filter branch. Nice. It will do some history-altering action that we give it to every commit in that rev list, and it will do some changes, overwrite the commits, get rid of the old ones, and not affect your other branches for now. Now, possibly, you're sitting there thinking, hang on a second, those blue commits just disappeared, and they were overwritten by pink commits. Detective Kadel, are they, I've learned something earlier, are they sort of still there? Well, yes, class. Well done, cadets. Gold star for you. Because they are. For now, those commits that just seem to be eviscerated from existence are still there. They're sort of unreachable, but they're not. You'll understand it in a second. We can use the git showref command, which is an awesome command, lists all of the human-readable references like branch names, tags, etc., and which commit those refs point to. And here we can see something interesting. There's this refs, original refs. I've not made that. Git automatically made that. And in fact, inside those original refs are my blue commits that I thought I'd just lost forever. And because although filter branch is a terrifying, scary monster, it's protecting us. I guess it's just trying to be a good guy. 2 of you got that reference. I'm very upset. It's fine. Rick and Morty, check it out. Anyway, and what about Git garbage collection? Well, Right now, there's this reference pointing at our blue commits. So if we ran the garbage collector right now, they are protected from annihilation. And in fact, we can use that weird reference string to check out our old changes. So they've not really gone anywhere yet. All up until we use something that updates our references and potentially deletes that little protective wrapper around those commits. Now, when the garbage collector runs, it will AK-47 those blue commits out of existence. I love kicking things, imaginary things. So, interesting. Back to filter branch, right? The other side of filter branch is the filters. And filters is a weird thing. It's basically the area, the scope of history that you want to manipulate, right? I'll explain a little better in a second. There's loads of different filters, and you can combine them together. We're going to look at two. Message filter, because it's super easy and it will help you understand filter branch like this. Easy. And then index filter, because it's the useful one. So, message filter. The scope of history, the scope of change that it affects is just the commit message. That's it. So you can see the filters just focus in on one area. The command that we give it, so we say what it wants to manipulate, how it wants to manipulate, it takes as standard input the original commit message, and whatever it spits out to standard out is our new commit message. Let's see some examples. Here we're doing message filter, and in the quotes after it is the string echo glory to superearth. Sorry, the command glory to superearth. So every commit message will be glory to superearth. Now, I'm not entirely sure why you do that, possibly because you're a good democratic patriot. Helldivers reference. Helldivers reference. Oi, 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 sorry. I thought you guys were nerds. Come on. Anyway, examples. But some better examples. Remember, we take as standard input the original message, so we can manipulate that original message. And here, I'm just doing a sed command that adds little hyphens around the commit message. Again, not sure why you'd want to do that, but examples. Or we could base 64 encode our commit messages, and they'd look like this. Kind of looks familiar. Anyway, let's move on. So before we do our filter branch command, we have our list of commits. We've got D27 here as an example to look at. After we've run the command, we have both our original D27 commit and our new modified commit. Now, what's important to note is that both commits have the same author. The author didn't get overwritten. We only want to affect that tiny piece of scope, that tiny filter. And even more importantly, both commits point to the same tree object because we didn't change anything but the commit message. Yum. Now, over to index filter, the important one, right? The index filter, the scope of change of history it affects is just the index of a commit. And that's basically just the files that the commit knows about in that moment. And you can always query that information using the ls-files plumbing command. So if it affects the index, let's have some examples. We could do index filter and then the command after it, git add and another file that exists somewhere else on my machine. And that would make it as though that file had always existed throughout all of time. You just didn't pay attention, silly. Or the more important example is git rm file, so remove file. And that would make it as though the file was never there. It was never there throughout history. You didn't see anything. And that's the important one. That's the one we use for secret removal. Now, this terrifying command, should be one line, by the way, but it's way too long, is a copy and pastable secret removal command. You can copy and paste it and use it. I promise. Guaranteed. But we're going to break down each bit so you understand it because it's really not scary when you understand it. Here, we're actually using two filters. Remember, you can combine one or more filters. We're using index filter and tag name filter. Each filter in the yellow box after it has the actual manipulation that it's running, the command on that filter, on that scope of history. So let's look at those. Index filter we've just seen. Git rm, ignore unmatched is awesome, by the way. So if you run git rm and say a file that you want to remove, and it can't find that file because it doesn't exist, usually it would fail. But with ignore unmatched, it's just like, oh, it's not there. I'll carry on. Because maybe that secret file has not always been there throughout history. Maybe it was added later. Delicious. And then the path of the file you want to nuke. Then there's tag name filter. So the scope, the area of change that it affects is just the tag names. So how the tags are named. As standard input, it takes the original tag name, and as standard output, it takes the new tag name. And with this cat thing, it's basically just taking the standard input and passing it right back out. No name is changed, it just passes it right back out. And this is because tags point to a specific commit. And maybe that commit just got destroyed, right? So now we just need to make tag name go, hey, tag name, yeah? Point over there. Oh, yeah, it's that commit now instead. So just updating where the tags are pointing to. There's some awesome options here for the filter branch command itself. Prune empty is awesome because if the original commit only added like that secret in the past, right? That was the only addition. And now that secret is gone, that commit's empty. We don't want an empty commit in our history. What a waste of space. So get rid of it. There's force, because again, this shows that filter branch is trying to protect us from ourselves. Without this flag, if filter branch runs and it sees there's original refs backed up, it'll go, oh no, there's original refs, buddy. Well, I'm not doing anything. You're on your own. But with this force flag here, you go, hey, filter branch, I'm crazy. Overwrite them. Let's go, right? Then there's --, which is a Unixy thing to basically tell the command, hey command, I'm done giving you options. You're about to get the all-important argument. And in this case, it's a rev list, which is --all for all branches, all tags on your repository. So this copy and pastable command will remove a secret from your history locally. Now, if you run this command and you're like, oh, I'm not sure if I've done the right thing, then don't panic. Because there's time, there's still time. Like actually, there is still time. When you run this command, it doesn't actually do anything for the first 5 seconds. It gives you a little message like, hey, if you didn't mean to run this, then hit Control-C. It's fine, you can do that. And look, it even sort of points back to that other repository. So don't panic, there's still time. But if you let the command run, the 5 seconds passes and it does all its crazy nonsense, you're like, oh, I'm not sure if I did the right thing, then remember, filter branch is a good guy. It's backing up those changes that we've just destroyed in the original refs. You can always check them back out, and there they are. No trouble. Now, unfortunately, the last piece of the puzzle is those other criminals that exist around the world, the other developers. How do we get the new rewritten history to them? And unfortunately, the only way is by force pushing. You should never force push. Except for now. Because we've rewritten history, we have to force push. And --all says force push everything. Hey! And the only bit of advice that I can give you here is to do this bit with your team, in the same room, on the same call. Do it in front of them, let them see the outputs, the inputs, so they know what's going on, so they know to prepare themselves for the chaos that comes.
Detectives! It was base 64 encoded.
Base 64, Refi! Of course it was base 64. I knew I recognized that. Okay, we can decode that. Here we go, Refi. Let's decode it and see if it says anything. Oh, Refi, it's plain text, and it's a confession. We've got him dead to rights. It was me, your partner. Refi?
I'm sorry, partner. It was either me or you. I didn't have a choice. He told me he'd revert my child commits if I didn't do what he said.
Refi, how could you do this to me, partner? We've known each other for years. You should have spoke to me. I could have helped you. Who even is this guy?
All I know is he goes by KB. He looked just like you, but with a mustache.
Refi, you gotta help me, buddy. I'm not gonna make it. Refi, please.
I gotta go.
Refi.
I'm sorry.
Refi, no! Refi! Refi! Thank you all so much for coming to my ridiculous talk. I hope you enjoyed it. Again, links to everything I covered in that link tree. QR code takes you to the same place. There's loads more resources in case you want to learn more. Socials are on the screen in the bottom left there. Excitingly, I'm one of those assholes that has my own branded merch. So if anybody's interested in a Ben Kadel pin, a Ben Kadel sticker, a Ken Bedell sticker, or the limited edition for this year, the Refi stickers, then I have very limited supply here. Please find me after this talk in the conference somewhere, and we can deal with that. Can I just ask, how much time have I got left? 0. Well then, okay, forget the next bit I was going to do. Check out the Pin Droid Twitter as well to find yourself some droids. Thank you so much for coming. Have a great rest of DroidCon.